All right, so we're going to start with number 4 here. How long does it take an automobile traveling at this to become even with the car traveling in the other lane at this? Cars front bumpers are initially this far apart. All right, now, how many different frames of reference are there here? How many? 3 different frames of reference, right? You've got the ground, we've got automobile number 1, and we've got automobile number 2. All 3 of those are in separate frames of reference. So the question is, which frame of reference do we want to use? And there isn't a correct frame of reference to do it in. We could do it in any of the 3 and have it and come out to the same answer. Because time is shared commonly between all of these. And that's probably how I'll start off my why, is saying there's 3 frames of reference. Time is the same in all 3. And then I'll pick one to do it in. So, which one should we do it in? Which one do you want to do it in? You want to do it from the grounds? Okay. We can do it from the grounds frame of reference. From the grounds frame of reference, the ground isn't moving, and both cars are. And when they ask, become even with the car, that means they're at the same place at the same time. All right? So actually, and I'm not trying to dissuade you, but doing it from the grounds, in a sense, I find it the most tricky because I've got 2 things moving, and I care about where both of them are. You know. For what? Yes. Okay. Do you guys? Does that work? Do you guys mind if we do it from the second car, the slower car? All right. So let's do that. All right. So this is number 4. I would start off with 3 frames of reference. And I normally abbreviate frame of reference because I get tired of writing it as capital F, lowercase o, capital R. So if you see me writing that, like in problem solutions or anything, that means frame of reference for me. So there's 3 frames of reference. They share common time. And then I'm going to change to from car B frame of reference. Let's see, from car B's frame of reference. Car B is still, right? Then whatever frame of reference we're in, we're not moving. Yes? Ground is moving to the, it's moving negative. Can we say that? Ground is moving neg. And car A is moving positive. So, and I usually, I'm because of how visual I am, I need to draw myself a picture of what this looks like. So, I might even, so let's see. This would probably still be part of my why, but I'm going to draw, here's car B. And then let's do this. Here's the ground. And the ground is going to be moving that way. Velocity of the ground with respect to car B. And then we'll have car A. Nice fast car. And car A would be moving this way. The velocity of A with respect to B. No. Yes. Does that make sense? From car B's to reference. They're not moving. The ground's going that way, and car A is coming at them. Yes? Okay. So velocity of the ground with respect to car B. Yeah. All right. So let's see what they tell me in the problem. I'm going to convert. Yeah, I'm going to convert that distance to kilometers because I'll either have to convert. Oh, yeah. I'm going to convert the distance to kilometers, and then I'll get an answer in hours, and I'll convert that to seconds. I could go through. Would it make you guys more comfortable to convert 64 to meters per second, 30 to meters per second? I'd rather convert the last to kilometers, because converting to meters per second is going to give us a nasty number. All right? Huh? Yeah. Okay. So, the first velocity I'm given is the velocity of A with respect to the ground. So that's the velocity of A with respect to the ground is positive 64 kilometers per hour. Then I'm given the velocity of B with respect to the ground. Ooh, the velocity of B with respect to the ground, and that is 30 kilometers an hour. Positive. And I think that's all I'm told. Oh, I'm told my distance, right? Mine is 112 meters, so that's 0.112 kilometers. Converted from kilometers to meters, right? Three. Yeah. And there's 1,000 meters in a kilometer. Wow. Alrighty. So, what I need, so I need to remember my relative motion formulas, which was that I had two of them. Velocity of A, D equals the opposite of velocity dA, right? And I also had the velocity of AB plus the velocity of BC equals the velocity of AC. Those are my two equations from my equation sheet, right? And so I want to use those. I need to find out the velocity of A with respect to B. So I know how fast A is coming at me, then I can tell how long it's going to take to cover that distance. Okay? So, now some people might be able to do that in their head, but this is how you actually do it. I want to end up with the velocity of A with respect to B. So over here I'm going to have the velocity of A with respect to something plus the velocity of something with respect to the B. And the thing they share in common is the ground, right? So it's going to be velocity of A with respect to the ground plus the velocity of the ground with respect to B, and I'll get the velocity of A with respect to B. Remember, I look at what I want, and then I work backwards to figure out where I came from. So let's see. Oh, I know this first one, right? It's positive 64 kilometers an hour. But what I need is the velocity of the ground with respect to B. Oh, I can use this side, right? So if the velocity of B to G, that equals the opposite of the velocity of G to B. So this must be negative 30 kilometers an hour. Yes? No? So that means my velocity of car A with respect to car B is 34 kilometers an hour. I didn't even have to follow my calculator yet, have I? So I know if I'm in B, I'm seeing car A come at me at 34 kilometers an hour, and I want to know how long it's going to take to cover this distance. So I'm going to use D equals D naught plus V initial T plus 1/2 A T squared. No acceleration, so that goes away. And say where we started was 0. So I'm left with 0.112 kilometers. Is that right? Yep. Equals 34 kilometers per hour times T. Why did I cross out what? Because how much is it accelerating? None. So 1/2 times 0. 0 times T squared. 0, so just forget about it. Forget about it. And now I solve for T. So this is where I'm going to pull out my calculator and do 0.112 divided by, what did I have there? 34. 34. And I will get that many hours. Not many hours. Small number. So I don't feel like writing that small number. I'm not done yet. That's hours. What does it ask for units of? Seconds. So I got to convert that to seconds. How do I do that? Well, I multiply by, is there 60 seconds in an hour? Not 360. I multiply it by 60 seconds in a minute times 60 minutes in an hour. Try it. Try 60 times 60 on your calculator. Got a 0 there. And that's what my answer is, 11.9 for me with scientific rounding. So I get 11.9 seconds. Let's hope that's right. After all, it is Monday. Most of the day. All right, let's look at number 2. Number 2 is very, very similar to number, whatever one we just did. What was it? 4? But in this case, our cars are moving in opposite directions, right? Eastbound and westbound. So again, we have 3 frames of reference. And we need to consider, they're asking us to consider the velocities from 2 of these different frames of reference. We have the frame of reference of the ground, we have the frame of reference of the of each of the cars. So what I would do is my Y for this, I'm going to draw 3 separate diagrams, one from each frame of reference. All right, number 2. This is number 2. And because I think that will help me the most, and it will show my understanding the most. So let's see. We'll draw the ground in green. We'll have car. So this one is going to be from the ground's frame of reference. Then we'll do it from car A's frame of reference. Problem 2. Problem number 2. And then we'll do it from car B's frame of reference. The cars are turning into looking like fixed wrestling cars. Here, G, ground. G. Alright, so, on the road, 2 cars moving opposite direction, approach and pass each other. Car A is in the eastbound lanes, moving with a speed of 12 meters per second. From the ground's frame of reference, the velocity of A with respect to the ground is that way at 12 meters per second. B is in the westbound lane, moving with a speed of 25 meters per second. So this one is now moving this way. This is the velocity of B with respect to the ground, and that is that direction, 25 meters per second. Watch. Make sure you have your own values in there, right? And which way do you guys want to call positive? East? Okay, so we're going to go a big old positive that way. So now, with respect to car A, and remember this is our car A here, A is not moving, but the ground would be moving that way, velocity of the ground with respect to A, and car B would also be moving this way, the velocity of B with respect to A would be that direction. And then if we're car B would see the velocity of the ground with respect to B, and it would also in that same direction see the velocity of car A with respect to B. Right? Yeah? Well, because if I'm in car A, I'm seeing the ground coming towards me and car B coming towards me. And if I'm in A and if I'm in B, I'm seeing both those things coming towards me too. Yes, VBA. Sorry, my B got a little buxom. That's a B. Kind of. Parents, what were you asking? That's the velocity of the ground with respect to B. The blue arrow in the middle? Okay, yeah. So, now let's see what they ask us. What is the magnitude and direction of the velocity of car A as seen by the driver of car B? So we're in the reference frame of B now, blue reference frame, and we want to end up with, remember, our equations here are velocity of AB plus velocity of BC equals velocity of AC, and we've got that velocity of AB equals the negative of velocity BA. So, from B, we we want the velocity of AB. To get that, we need the velocity of A with respect to the ground plus the velocity of the ground with respect to B, and we can get the velocity of A with respect to B. The velocity of A with respect to the ground. Some of you is probably looking at this going, I just did it in my head. That's fine, but this is how we actually do it. Velocity of A with respect to the ground is positive 12 meters per second. The velocity of the ground with respect to B, we didn't know that, but we know B to the ground, which is negative 25 meters per second. So this is plus 25 meters per second because it's opposite it, and that's going to equal 37 meters per second. Positive. Remember that positive means to the east. It's 25 because the velocity of B with respect to the ground is 25 meters per second positive, or negative, sorry, negative, because it's moving to the west. Now, that means the velocity of the ground with respect to B is positive 25 meters per second. Right. And that's good because we had it going that way. We expect a positive answer, and we got a positive answer. So we can do a little happy dance. But we should get positive 37 meters per second. And now they want the velocity of B as seen by driver A. So we do this whole... Yes, it's positive, so it's going east. Yep. Now we're going to do the same thing from the reds. And we want the velocity of B with respect to A. Oh, wait a minute. If I want the velocity of B with respect to A, I've got the velocity of A with respect to B. What do? I reverse it. So it'd be negative 37 meters per second. Or the other way to say that, 37 meters per second. West. Hope that works. I don't know. Let's see. So I have 37 here. And I'm saying that's east, and I say 37 here, and I'm saying that that's west. Cross fingers. Yay! All right, let's do number 3, because number 1 is very similar to the other 2 we've done this block. So let's look at number 3. You've got this boat. This is a lot like that activity we were doing the other day, right? So I would probably, the main things I would do here in my Y is I would definitely do a vector diagram. Saved nicely done for us. So let's go ahead and capture that, just since they were so nice to have already kind of diagrammed it out. And we'll keep some of that. This is number 3. What do you mean get the numbers? Use your numbers, Sean. All right, so the boat is pointing its prow directly across the stream, and the boat can travel, in mine it's 2.3 meters a second in still water, across the stream whose current is this. So in my vector diagram, that's telling me that this side is 2.30 meters per second, and my other side is 1.2, and this side is 1.20 meters per second. We're going to get there, yeah. But notice how the vectors do add, just like we were talking about, right? Velocity of the boat with respect to the water, plus the water to the shore gives you the boat to the shore. So we're adding the two vectors. So I would put some things along the lines of the two velocities do not change each other, but combine together. Now, the one thing I didn't think they were very clear in this problem is the direction that they wanted. When they ask here, they ask for both. You look the velocity, which so they wanted the magnitude, how big is it, and also in what direction. And they say relative to the shore. On our vector diagram here, they're actually looking for this angle here. We'll call this angle alpha. That's the angle that they want. Now, if they had said relative to straight across, then they would want theta here. But we can actually find theta and then use that to find alpha, right? I made the mistake. I thought they wanted the angle downstream. It would have been better to say maybe the angle with respect to downstream or something. Because they told me the velocity of the boat with respect to the water is 2.30 meters a second. Look at how they worded it. The boat can travel 2.30 meters a second in still water. Think back to the exercise we were doing the other day, and they said, you know, they used all sorts of words like to the water molecules, to the tube, to, yeah, always saying with respect to the water. All right, so, yeah, so now I need to find how big velocity of boat with respect to the shore is, and for that, I'm going to use Pythagoras, our good old friend a squared plus b squared equals c squared, right? And my sides of my triangle are 2.30 meters per second squared plus 1.20 meters per second squared equals VBS squared. VBS equals. So let's see. 2.3 squared plus 1.2 squared. Enter. Second square root. Second answer. Enter. 2.59. Let me grab all of that. And so, of course, rounding that to 3 figs, I get 2.59 meters per second. Huh? Really? That's the velocity of the boat relative to the shore, yeah. Huh. Let me see what you did, Kurt. Did you get a negative answer for some reason? And now I'm going to figure out theta and then subtract theta from 90 to find alpha. So theta, because I have to find an angle, I can only find an angle inside my triangle, right? So theta, oh, I know the opposite side, and I know the adjacent side. So the relation between opposite and adjacent is tan. Let's do a different color here. So tan of theta theta is the opposite. Did it work, Bears? Over the adjacent. So tan theta equals my 1.20 meters per second over my 2.30 meters per second. And so to get theta, I do the inverse tan of both sides. And I get a theta of, that second tan 1.2 divided by 2.3. I get a theta of that. No, I have my big one. No, that means that you did the radians, right. There's calculators up there in the cabinet marked for pool balls. And the actual answer I want is 90 minus theta, which ends up 62.4. Because of, so my velocity is 2.59 meters per second at 62.4 degrees. Let's hope that's right. It's the 90 minus because alpha plus theta equals 90 on that diagram that I did. I can show you in a minute. 2.59, 62.4. As soon as I see if I'm right or not. Yep. So the one other factor, and we didn't put this in our Y yet, is the fact that the displacement and the velocity have to be in the same direction. So your displacement and your velocity in these cases would have to be in the exact same direction. Sure, sure. When I pause the video.